Section 4.4 is the multiplication rule of probability. There's an important distinction between the previous section and this section. In particular, when it comes to the notation probability of A and B occurring, in the previous section, we considered A and B as occurring as events in the same trial. So for example, you roll a pair of dice once, and perhaps A is the event we get a 1 on one of the die, and event B is the event that we roll a sum of 7. But we consider rolling the dice just once, one trial. In this section, we're going to be considering these events occurring on successive trials. So A, the probability of A happening and then B happening. Two different trials. So in other words, if we're talking about rolling a pair of dice, we'd roll it once and A would be the event something happens. Then we'd roll the dice again and B is going to be the event something else happens. So keep that in mind as we discuss the multiplication rules for probability and how that differs from the previous section, which was the addition rule for probability. It's one trial versus multiple trials. So again, we say the probability that A and B occur is the probability that A occurred in a first trial and B occurred in a second trial. But again, we use the same notation. Either we say the probability of A and B, or you'll see this notation, the probability of A intersect B. For example, suppose we flip a coin 3 times. We'll let A be the event we get a head on the first flip, we'll let B be the event we get a tail on the second flip, and we'll let C be the event that we get a tail on the third flip. Find the probability that A happens, and then B happens, and then C happens. Well, in the previous sections, we might have been able to, say, consider the sample space, and notice there's 8 different simple events in our sample space, and then think about which one of these is our event, our event that A and then B and then C occurs. Well, of course, that's just the HTT, heads, then tails, then tails. Since there's only one way for that to happen, out of 8 total possible simple events in our sample space, the classical approach to probability tells us that the probability of A and then B and then C occurring is 1 divided by 8, which is 0.125. Another way to calculate this, you might have noticed, would be to just multiply the probability that A occurs times the probability that B occurs times the probability that C occurs. So of course, the probability that we get a head on the first flip, that's just 1/2. The probability that we get a tail on the second flip, again, that's 1/2. And the probability that we get a tail on the third flip, 1/2. So if we multiply all these together, that's 1/2 times 1/2 times 1/2, which of course is 1/8, which again is 0.125. So we had 2 ways to calculate the probability. However, it turns out that you can't always just multiply the probabilities of each event in order to get the probability that all 3 events happen successively. Let's look at another example. Suppose we have a box here, and I'm going to throw some circles into this box. So I'll throw 1, 2, 3 red circles in, and we'll throw 1, 2 orange circles in. We'll let A be the event we pull an orange circle out, and let B be the event we pull a red circle out. If we want to find the probability that A happens and then B happens, can we just multiply the probability of A times the probability of B? Well, let's think about what this is. The probability that A occurs, in other words, the probability that we pull an orange circle out, since there's 2 in there, out of 5 total circles, the probability would be 2/5. Similarly, for the probability of B occurring, the probability we pull a red circle out would be 3, because there's 3 red circles, divided by the total number of circles, which would be 5. Multiplying those together, you'd get 6 out of 25, which is 0.24. That's actually not correct. So consider this. Again, we're finding the probability that A occurs and then B occurs. So let's start with the probability of pulling an orange out. If we pull an orange out, now think about how many circles are left and how many red circles are left. Then we can get the probability that we pull a red circle out. Since there's only 4 circles left and there's 3 red ones in there, the probability that we're going to pull a red circle out is 3/4. But now if we multiply these together, we'll get 6 out of 20, which is 0.3. Clearly a different answer than if we just multiply the individual probabilities together. So what's going on? Well, let's first talk about this concept of conditional probability. That is, the probability of some event B happening once we already know that A has occurred. That is a conditional probability. So for example, if we let A be the event that you win the Mega Millions jackpot, and we let B be the event that your friend wins, think about what this means. If you won the Mega Millions jackpot, does that affect the probability that your friend would win? And recall that winning the jackpot means you've just chosen the numbers on the Mega Millions lottery ticket correctly. So you winning has no bearing on what your friend wins. They can pick any numbers they want. It's independent of what you picked. So we'd say these events are independent. So if we consider the conditional probability, that is, the probability that your friend wins given that you have already won, well, that's just the same probability that your friend wins because your winning had nothing to do with the probability that they'll win. So again, we call these events independent if one event does not affect the other event. Or rather, the probability of one event does not affect the probability of another event. So the multiplication rule for probability, the probability that A occurs and B occurs is the probability that A occurs times the probability that B occurs given that A has already occurred. If A and B are independent, however, we have the more simplified probability. Probability of A and B occurring equals the probability of A times the probability of B. So suppose we flip a coin twice, and we let A be the event that we flip a head on the first trial, and let B be the event that we flip a tail on the second trial. Well, the probability of A is 1/2. The probability of B, given A has already occurred, since these are independent, in other words, the first flip has no bearing on the probability of the second flip, we say that the probability of B given A is the same thing as just the probability of B occurring, which in this case is 1/2. So the probability of A occurring and then B occurring is 1/2 times 1/2. In the ball example, however, or the orange and red circle example, if we let A be the event that we pull an orange ball out, and then B be the event that we pull a red ball out, and specifically, I'm going to mention this idea of without replacement. So in other words, suppose we pull suppose A occurs, and we pull an orange ball out, the probability of that occurring is 2/5, since there were 2 orange and 5 balls total. The probability of B was 3/5. Since the probability of B changed once we already picked out an orange ball to 3/4, we have to change the probability of A and B to reflect this. A similar situation, but slightly different, if we go back to the ball example again, let A be the event we pull an orange ball out, let B be the event that we pull a red ball out. However, this time we're going to consider with replacement, meaning we pull the orange ball out, but then we put it back. In this case, once we put it back, then the probability of B doesn't change given that A has already occurred, because once we put that orange ball back, all the probabilities reset to their original probabilities. What is the probability that we roll a die 3 times and each roll is a 1? Well, since die rolls are independent, meaning one roll doesn't affect the probability of the next roll, then if we consider A to be the event that the first roll is a 1, B is the event that the second roll is a 1, and C is the event that the third roll is a 1, since these are independent, the probability that A occurs and B occurs and C occurs is just the probability of each one multiplied times the other. So probability of A times probability of B times the probability of C. If we roll a die twice and both times we got a 1, what is the probability that we roll it a third time and get a 1? Well, you have to be careful here because since we already know about the first 2 die, and since they don't affect the third roll, then the third roll is just 1/6 probability that we'd get a 1. If you have 8 children, what is the probability that each child is a girl? Well, consider each child to be a separate event. And note that having a child is independent from any previous children. So we consider several events, and we're talking about the probability of A occurring, and then B occurring, and then C occurring, and then etc., 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 8 different events. But since they're independent, the probability of these things occurring one after the other, or rather having a girl occurring one after the other, is just 1/2 times 1/2 times 1/2, 8 times. And of course, mathematically, a more condensed way to write this would be 1/2 to the 8th power. So calculating this, we get 1 out of 256, or 0.0039 probability of having 8 girls. If you have 5 children, what's the probability that you have a boy, and then a girl, then a girl, then a boy, and then a girl? Well, the idea is the same. So in this case, we consider 5 separate events, but again, having children is independent from having any previous children. So the probability of having a boy is 1/2, the probability of then having a girl is 1/2, etc., 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 5 times. So we just have to calculate 1/2 to the 5th power. And that is, there is a 1 out of 32, or a 0.0313 probability of having a boy, then a girl, then a girl, then a boy, and then a girl. If you roll a die 4 times, what is the probability you roll a 3, and then a 5, and then a 6, and then a 2? Well, here we'll consider 4 separate events, rolling the die 4 separate times. Since the probability of rolling a die is 1/6, the probability of rolling a 3 on a die is 1/6, which is the same for rolling any other number on a die. And every time you roll a die, the probability of some number coming up is independent of what happened previously. We just have to take 1/6 times 1/6 times 1/6 times 1/6 to get 0.0008 of getting that exact sequence. So let's go back to the ball and box example. So this time I'm going to throw some red balls in the box, throw some orange balls in the box, but then start throwing a lot more in. So we do this over and over again. So finally, suppose we had 600 reds and 400 oranges. We'll let A be the event that we pull an orange ball out, and we'll let B be the event we pull a red ball out. What we want to know is what's the probability of A occurring and then B occurring. Well, like we said before, assuming we're talking about without replacement, so this time our ball we're not going to put back in. Suppose A occurred, the probability that A occurs is just 400 out of 1,000, because there are 1,000 balls in there and 400 of them are orange. So the probability of A is 0.4. The probability of B is 0.6. However, since we're sampling or we're pulling the ball out without replacement, the probability of B, given that A has occurred, is 600 divided by 999. Since there's still 600 red balls in, but only 999 total balls in the box. So to calculate the probability that A occurs and then B occurs, we simply multiply probability of A times the probability of B given A, which is 0.4 times 0.600, etc. This gets us a number close to 0.2402. Suppose we instead made a mistake and just multiplied the probability of A times the probability of B. We instead get 0.4 times 0.6, which is 0.24. Now compare the two answers, the mistaken answer, which is 0.24, and the actual answer, which is 0.2402. There's a 2/10,000ths difference between these two numbers, which in statistics is fairly insignificant. So we have a rule of thumb that tells us when we can treat dependent events as independent. In other words, we can do the calculation the wrong way under certain conditions. Treating dependent events as independent, we have a 5% guideline. If the sample size is no more than 5% of the size of the population, we can treat the selections as being independent. So as in the previous example, our sample size was 2 since we were only pulling 2 balls from the box, and our population was 1,000 since there were 1,000 balls in the box. We can treat the event B as independent of event A since 2 out of 1,000 is 0.002, which is certainly less than 0.05 or 5%. As a preview to one of the applications we're going to be using these probability ideas for, something called hypothesis testing. So it's something we'll be doing a lot of later on in the semester. But take a look at this example as a preview. A company called Microsort has an XSort gender selection technique which is designed to increase the likelihood that a baby will be a girl. Now suppose that in a test of the XSort method, 20 couples give birth to 20 babies, and all 20 babies were girls. If we were to assume that the XSort method has no effect, in other words, having a girl and having a boy is just a 50-50 chance, or in other words, the probability of having a girl is 1/2, then what is the probability of getting 20 girls in 20 births just by random chance? Well, of course, we already know how to figure this out. This would be 1/2 to the 20th power, which is 0.00001 probability. Now that is so small that we actually use this notation 0+ to say that there's a 0% chance probability that we'd have 20 girls in 20 births. The plus is to indicate, well, there's still a small chance that it could happen. But otherwise, we take it to be 0. Almost impossible.